We start recording of lecture 9 in our class. We go directly to the screen share, and what we are going to cover today is a chapter on the risk index and safety indices. So we go to our web text here, and we open the chapter on incidence and risk indices. We're supposed to share the screen. We are going to introduce the concept of an index. The index is a way of assessing the level of risk of safety in our case, similarly to the case of the Richter scale or the Torino scale that are introduced in assessing the level of damage that can be caused by natural phenomena. But our approach applies to any kind of societal activity, as we'll see. However, we will separate between what we are going to call incidence indices, as this would be applied for the risk assessment of a large population that is subjected to some form of common hazard, such as disease or natural disasters. However, if we have a limited size population, then we cannot apply the same criteria or the same assessment to a limited size population that we apply to a large size population. So in that case, we are going to use a more appropriate likelihood indices, which are derived for the comparison of hazardous activities that are peculiar to a small group of people that are engaged in a hazardous, or they are subjected to some form of a hazard, like say, chemicals produced in a chemical plant or radiation in a nuclear power environment. The approach has a large domain of applicabilities, as we'll see in the examples. It matches intuition and provides measurements of the level of safety or the level of risk on a logarithmic scale. Every unit increases the incidence in the incidence safety index correspond to a risk decrease by a factor of 10. So in that case, we are using the logarithm to the base 10 rather than the logarithm to the base e, or 2.718, which is designated as ln for natural logarithm. Our logarithm is simply the conventional logarithm to the base 10. And in that case, you find that the value of the risk indices or the safety indices basically are contained in the range or the interval 0 to 10. You'll find there's an illustration, two illustrations in the analysis of the hazardous activities in a large population. We use the Beaufort wind scale as relevant in the monitoring and control of wind turbines, and to the unemployment situation from the local, regional, and national perspectives. That approach can lead to useful insights in the allocation of resources, remedial actions, monitoring, and control strategies from the proposed indices can be deduced on a logical and objective basis. So the mathematical basis has to do with the logarithm to the base 10. The logarithm to the base 10 of a number x is the power to which 10 must be raised to equal the number under consideration. So if you have a number x, you take 10 to the power of n. If you take its logarithm, the logarithm of x to the base 10, that's a log of that 10 to the nth power to the base 10, which is the same as n, the natural logarithm, the base 10 logarithm to 10. And we have to remember that the log 10 to the base 10 is simply 1. So the log of 10 x to the base 10 is simply that exponent of the 10 factor small n. So we have to remember that log 10 to the first power is 1 then, and log 1, which is the same as log 10 to the 0th power, is a 0. A simple numerical example here. If you want to calculate the log to the base 10 of 100, that's like 10 to the second power, it's immediately 2. And if you have the log 10 to the base 10 of 1000, that's like 10 to the third power, oh, it's a 3. If you have a number that's intermediate between the 100 and 1000, that is log to the base 10 of 500, and that becomes 2.699. Along this line, we define what we are going to call the incidence safety index. If you remember, incidence here applies to a large population, like the population of the United States, for instance, in terms of certain hazards like heart disease or deaths from cancer and accidents, motor vehicle accidents. So in that case, for a large population of a number of people T, if you consider the ratio of the number of deaths per person per year, so it's deaths per year, this statistic is available, and you divide by the number of persons, the F factor, in that case, we're going to define it as a frequency, is the number of deaths divided by per year divided by the number of persons involved. On that incidence factor here, we can define what we call the safety index. It's simply the log to the base 10 of the inverse of the value of F. So in that case, it becomes the log to the base 10 of the T divided into D, which is the same as minus the log to the base 10 of D over T. In fact, it is just 1 over F. Or you can write it as minus the log to the base 10 of F. This is a mathematical symbol for all values of F not equal to 0, because if you take the logarithm of 0, it becomes minus infinity. So everything is defined except when there are no deaths, or in that case, the number F is equal to 0. So this safety index only applies when F is not equal to 0. That's what we mean by that symbol right here. So in that case, you find that the less risky the activity or exposure, the higher the value of the safety index on a scale from 0 to 10. On the other hand, the more risky the activity of the exposure, you'll find that this is lower the value of S sub I. So in that case, we can also define immediately an incidence risk index. So this is a safety index. The risk index would be 10, the maximum number on the scale, minus the safety index. So it becomes 10 minus log to the base 10, 1 over F, which is the same as 10 plus the log 10 to the base F for all values, again, that are not equal to 0. And this very much bears resemblance to the Richter earthquake magnitude scale, where the larger the magnitude of the detected seismic signal on a seismograph, the larger is the expected damage from the earthquake, except that the Richter scale takes an arbitrary number of subdivision, 1 to 12 or 1 to 15, whereas here we are defining a range of 0 to 10, which is much more suitable for comparing different levels of safety or of risk. A value of 10 on the scale corresponds to the safety index of 0 and or assured death. A low risk index corresponds to a higher safety index and vice versa. So in that case, you can look at the level of safety or we can look at the level of risk. Let us compare the risk and safety indices, and by applying it to an example in the United States, we have a population. Let's assume that we have a population of 300 million people. Like the actual population is 320 maybe, but just to simplify the math, we take a population of 300 million persons, And let us apply this concept of risk and safety indices. Now, this is an incidence type of risk calculation, because we are applying it to a large population, the whole population of the United States. Let's look at different activities that can cause death per year. We know the statistics for these numbers. Heart and circulatory disease kills on average 600, well, actually, these are the data for maybe an earlier year, so it's not for 2020 or 2021, but a typical number is for heart and circulatory disease causes the deaths of 624,000 people per year. So this is our D in the equation that we derived earlier. The cancer deaths are the second cause of death in the United States, 500,000. Premature deaths from smoking by heart and lung disease, 300,000. So you find that the heart, cancer, and then lung disease are the three large killers of people dying in the United States. That's followed by motor vehicle accidents. Unfortunately, half of them are due to driving under the influence of alcohol or drugs. For comparison, the number of deaths compared to the Vietnam War, that was 43,000. Accidental falls, people shoveling snow on the roof of their buildings, or maybe even elderly people falling while in a bathtub. So that's a dangerous activity there. Fires and hot substance, 7,000. Drowning, 6,000. Poisons, 5.5. The Iraq War caused the deaths of 3,000 troops. In that case, bicycle riding, 2,900. Acts of terrorism, 2,800. That's related to September 11, 2001. It doesn't occur every year, obviously. Firearms, 2,000. Machinery, 1968, 2,000. Air travel, that's 1,700. That's a comma here. Water transport, 1,743. Falling objects, 1,200. And we can go on for other minor activities that can cause deaths: electrocution, railways, lightning, hurricanes, tornadoes, kidnappings, and bee stings. You could see bee stings kill 47 people per year. So this is in our formula for the incidence. Incidence applies, so remember, to a large population. Now, we calculate the frequency here of deaths. We take the D, the number of deaths, and divide it into T, which is the total number of persons. It gives us units of deaths per person per year, because the statistics that we have are here, number of deaths per year. You divide it into the total population as T here, and these are the numbers that we get. Applying our formula for the incidence safety index that we derived earlier, so that becomes the log to the base 10 of 1 over f, the frequency that we calculated. We get these numbers here. For heart and circulatory disease, the safety index is 2.68, whereas you find that on the scale of safety, that is a scale from 0 to 10. However, you find obviously that the level of safety of bee stings is not that high. It is higher than definitely the cancer risk in terms of the deaths. So that's bee stings would be 6.8 only. And then we know that if we are not interested in the level of safety, but we are interested in the level of risk, then we take 10 minus the safety index, and you'll find that in terms of heart and circulatory disease, it's a kind of high risk. It is not 10, obviously it's not causing all the death, but it's 7.32. Notice that the incidence safety index and the incidence risk index add up to 10 in all the columns. And if you look at the risk index of bee stings, obviously it is a very small number compared to the deaths from cancer. So in that case, it gives us a scale from 0 to 10 of the different risks and or the safety levels of different situations in terms of deaths from different causes in the United States. Again, we would like to make a distinction between the likelihood and incidence risk and safety indices. The incidence, safety, and risk indices are an indication of incidence. They're not an indication of likelihood. They're useful for the assessment and comparison of common activities and exposures to hazards such as illnesses, and in general activities and procedures applied to a large population. So incidence applies to a large population. It should be noted that in the field of statistics, there is a distinction between probability, which allows a prediction of unknown outcome based on known parameters, if we have observations, and likelihood, which allows us the estimation of unknown parameters based on actual known income. Some hazardous activities such as, say, bungee cord jumping or skydiving or motorcycling are usually practiced by small populations. So it is not realistic to apply the criteria in terms of risk and safety to a small population that we apply to a large population. Very few people, for instance, in the United States die from skydiving. And if you want to look at the risk of skydiving or motorcycling, we look at the people who practice those sports, and that's a small part of the overall population. According to the likelihood of the activity can be more appropriately expressed by a modified index that considers for the size of the population, not the T in our original equation, by T prime, that would be the size of that limited size population that is performing a certain type of activity, and basically the population that is at risk from the activity. So it is more appropriate to consider the likelihood, safety, and risk indices, considering the same equation as we used earlier, but now the size of the population is the size of the limited population that is at risk. Example, if we have 10,000 people who practice skydiving and 20% of them, 20 persons among them die per year, then if you want to calculate the likelihood now, not the incidence, the likelihood, because it's a limited population, safety index, it becomes minus the log to the base 10 of the number of deaths divided by the number of that population, not the whole population of the United States, which if we do that, we'll get a very misleading number. So in that case, in that population, 20 people die per year, and the population itself is 10,000. So you get a safety index of 2.7, and the risk index would be 10 minus that 2.7. So in that case, you could find that for 20 people dying among 20,000 people, the risk index is 6.3. It is slightly below 10. And the safety index is 2.7. And notice that the safety index and the risk index add up to 10 in that case. Another interesting situation is a game of Russian roulette that has, it's named Russian because apparently it appeared among officers in the elite groups in the Russian army at the time of the Tsars there. And they would get influenced by being drunk by drinking too much vodka. So they meet together and try to show their courage. So how do they show their courage? By having a revolver with a 6-shot magazine, and one magazine only has a bullet in it. So they rotate the magazine, and then they pass around the revolver in that case, and shoot it at their head. And that was considered a sign of courage rather than being courageous on the battlefield. So in that case, you notice that the probability of death in that case is 1 in 6. It's almost like throwing a die. You get 1, 2 as outcomes 1, 2, 3, 4, 5, or 6. So 1 out of 6 attempts really is going to cause the death. So the level of safety in that case in the 6-shot magazine is 1 out of 6. So the safety, or in that case likelihood, is 0.78. We cannot go and consider the total number of deaths by Russian roulette in a large population, because it's only a limited population that is using it. So the activity itself would have a safety index of 0.78, rather low, and the risk index is rather high here, 9.22, a probability of death of 1/6. So this is a high risk, unwise, illogical, in fact, activity with a likelihood risk index of 9.22, close to its maximum attainable value of 10. And you could see how it meets our intuition here, that practicing Russian roulette is a very risky activity in general. We apply it here to another interesting application that would apply to engineering, maybe activities like the control of wind turbines. And the control of wind turbines depends on an index like the Richter scale.
Understand that.
Like the Richter scale, the Beaufort wind scale historically was developed for use by sailors and mariners on ships and boats. It was basically based initially on sea states, and then it was extended to the land effects of the wind. And in that case, you have a derived incident safety and risk indices, and can be used for monitoring for the implementation of controlled strategies of wind turbines. So the waves, the way the waves look for the mariners tell them about an impending coming storm. So, for instance, they could furl or unfurl their sails. They use sailboats. But in wind turbine operation, if the wind exceeds a certain design limit of the wind turbine, say 35 meters per second wind speed, that is a storm. And in that case, the control strategy is to turn off the wind turbines, contrary to intuition. And the reason for this is that at that high wind, the rotor blades of the wind turbine would rotate, acquire too much energy from the wind, and then you have the centrifugal force literally tearing apart, disintegrating the wind turbine. So as the wind speed increases, the safety index, in that case, you'll see as a translation of the Beaufort scale from 2 to 0 at the same time that the risk index increases from 8 to 10. So let's look at that Beaufort scale. The Beaufort number goes from 0, and you could see here that it goes to an illogical kind of 12, whereas our index here would translate into a scale from 0 to 10. So it's a more suitable scale that you can program into a program, and then in that case, that wind turbine is started or shut down. In the case of the Beaufort scale, it shows the speed of the wind at 10 meters height. 10-meter height is the standard height at which meteorological types of wind speed at airports are measured. So if the wind speed is from 0 to 0.4, the Beaufort scale describes the situation as calm. At 1, it's light, and until 5.8 meters per second at 10 meters height on the
okay, here's what I found online.
And in that case, you notice that when you reach the level of 9 or 8, even 21 meters per second, it is designated as a gale if you are using the Beaufort wind scale for the mariners on the waves in the ocean. The 29 meters per second, that's a strong gale. 29 to 34 strong gale, and larger than 34 miles, that's meters per second, I'm sorry, that would be a hurricane. Now, if you translate that Beaufort wind scale to the control of wind turbines operations, you'll find that you cannot really start a wind turbine with a very low wind scale. So wind turbines have a cut-in wind speed when they start rotating at about 5 meters per second. So in that case, at 3.6 to 5.8 meters per second, small size wind turbines get started. At 8.5 meters per second, that's the start of large wind turbine. You start operation at that level. At 10 meters per second is considered a good wind speed for wind turbine operation. So in that case, that's useful power generation at 1/3 of capacity. When you get to the 14 meters per second, that is the rated power range. This is what a wind turbine is designed to operate in. But when you start reaching the gale level and the Beaufort scale, the control mechanism is that you start shutting down your wind turbine. And if you get a strong gale, then at 25 meters per second, all wind machines have to be shut down, otherwise they'll disintegrate. At 29, this is the design criterion against damage. In hurricanes, all wind turbines will basically have undergo a serious damage. And we can translate even these kinds of observations that Mr. Beaufort, Admiral Beaufort in that case, has put together. You can see a correspondence between the wave shape in the ocean to the wind turbine effects to the land effects. If you are on land, you'll find that a wind speed of 0.4, you'll find that the smoke rises vertically. At light wind speeds, the smoke drifts, veins unaffected. Tree leaves start moving slightly at 3.6 meters per second. And in that case, in the case where you start at a strong 14 meters per second, you'll find that large branches start moving. At 25 meters per second, you start getting some structural damage in homes, like the shingles maybe will fly off the roof. At 99 meters per second, the trees are uprooted, much structural damage occurs. And at 34 meters per second, that's widespread damage. Above 34, which is a hurricane level winds, you get a disaster condition. So in that case, it's useful to have a scale from 0 to 10. And if we apply in that case, the fraction of the maximum in that case, if the maximum, the value is 0.0 to 0.4, you divide that by the maximum level of damage that you get at the bottom of the table here. So in that case, it's at 34. You go up and you can calculate in that case for d over t, the fraction of, take the fraction of the maximum, you'll find that you have a range of 0.0 to 0.01. Take the log 10 to the of 1 over f, and at the Beaufort number of 0, you get a safety index of 2, whereas when you attain the value of maybe here 0.39 to 0.3, then this is the full capacity operation of a wind turbine. You start shutting down the wind turbines at a scale of 0.21 to 0.13. Now, this safety index is the level of a scale from 0 to 10 of the levels of operation of wind turbines, translated from observation of the wave shape, like whether you find white bubbles on the tip of waves, and how the trees behave even on land. The level of risk, the risk index becomes 10 minus the safety index, and that is this, the safety. Actually, it seems that these are should be replaced by each other, because the level of safety would be 8 here, and the risk index is very low, should be 2. So the 2 columns, actually, I discovered just now, should be interchanged. At the hurricane level, which is the maximum value, you get that the risk is 10 and the safety level is 0. So it meets intuition if we switch those 2 columns. We can switch these ideas also to other social activities. You'll find that by redefining the activity on a scale of 0 to 10, we can apply it in a more convenient way. For instance, let's take the case of the level, the likelihood of unemployment in central Illinois. Notice now that it is a likelihood, that is not an incidence, because the population of unemployed people, of unemployment, say in central Illinois, does not apply to the whole nation. So in that case, the population that you are dealing with is a limited population. So it would be unfair to consider the whole population of the United States. In that case, we have a, you can look at central Illinois, the different counties in central Illinois, and you worry about the unemployment rate. And the government agencies in that case come in to try to help by providing funds for maybe re-educating or retraining people so that they can get meaningful jobs and lead a decent life in society. So let us say that there is a number of unemployed in central Illinois. These are the different county in Illinois: Champaign County, Coles County, Douglas County. The labor force side, or the people who are seeking jobs, is listed here. You notice Champaign County has the largest labor force in central Illinois, but you also have statistics about the jobless number. So in that case, the unemployment ratio, or the frequency, you take that D divided into T prime. Notice here, this is not an incidence, but this is a likelihood because it's a limited population. You can calculate the F as the unemployment ratio, and then the likelihood safety index would be the log to the base 10 of 1 over F. So in that case, you find that Champaign County, in terms of the level of employment or unemployment from the safety level, is 1.07. And you find that if you divide, you take the base 10, whereas the risk index is 8.93. However, if you go to another county, for instance, Vermilion County, you'll find that the risk index is 9.08. So in that case, there is a higher risk of unemployment in Vermilion County than Champaign County. And according to the likelihood risk factor, or the likelihood safety index, you allocate your funds to the location that needs the best or the higher level of help in terms of retraining and education to provide jobs in general. In essence, then, here we suggest a smarter way of assessing the levels of risk and the levels of safety in large populations. We designate it as the incidence risk or safety indices, and for limited size populations, we designate it as the likelihood indices. Somebody may think about for a different range of estimation, you can rederive the equations for a scale from 0 to 100, but we chose 0 to 10 here as a good choice for these ideas. The application of the concept of incidence of likelihood and risk and safety indices can be extended where the damage definitely is not just death, but could be unemployment, injuries, economic loss, or even environmental degradation in environmental types of systems designs. Other units of the risk estimate can be used, such as just probabilities. A different range of estimation is 0 to 100 for a large range of variation rather from 0 to 10. You can have it almost like a percentage in that case if you use the range 0 to 100. More specific risk could also be addressed, such as radiological risk, where other risk units prevail, such as the risk from the exposure of different effective doses of radiation, or the morbidity from, say, in coal mining or silicosis, the inhalation of risk in farmers. The slope of the deaths from cancer risk versus the radiation effective dose or dose equivalent is 8 10 to the minus 4, 7.9 10 to the minus 4 cancer deaths per person per year. So in that case, you can get a very good idea about the level of risk and the level of safety. The approach has a large domain of applicability compared with the more restrictive specialized indices like the Richter scale for earthquakes, as we have covered before, used in the measurement of earthquake magnitudes. It matches intuition and provides a measurement of the level of safety or risk in different situations. The methodology is applied to the analysis of the hazardous activities in a large population. The Beaufort wind scale, as applies to the monitoring and control of wind turbines and to the unemployment situation from the local, regional, and national perspective, have been given as examples. Useful insights for the allocation of resources, remedial actions, monitoring and control strategies can be deduced from these proposed indices rather than just depending on the raw data. In the same way that we depend on the Richter scale, not just at the level of damage to assess the damage, say, from earthquakes, or the Torino scale, or the Fujita scale for the incidence and the effects from tornadoes, for instance. As an exercise, I'm gonna request that you calculate the likelihood risk indices for obtaining the value of heads in the flip of a coin. That should be a very simple example, and obtaining a value of 6 in the throw of a single die. And this ends up that interesting application of risk indices in general. Thank you for your attention, and we